This is the recording for the Unit 3 homework, Energy and Momentum. Question 1, simply answer all of these with yes. You can read through these. Question 2 is the question that you take from the book and that you answer, and by now there are plenty of examples posted on the discussion board either by you or by other students, so you can easily follow them and figure out what the requirements are. It's really actually really easy. All this instruction here looks almost like an overkill. It's really easy. Take a question, type it out, figure out the answer. In this Unit 3, Energy and Momentum, Physics Content and Objectives, and you will see that all of these apply. They either make sense, yes, that's what's in the book. Respectively, I posted them in the Unit 3 folder in Lectures and Homework. Unit 4, Energy and Momentum. If you Google conservation laws physics, you would come across that these are the most fundamental principles in the universe. One of the first links is probably the hyperphysics one. Hyperphysics and Wikipedia are the go-to websites for me when I teach physics. So here are the quotes from hyperphysics. The momentum of an isolated system is constant. The vector sum of the momenta of all objects and so on. You can read this here. That obviously checks with conservation of momentum. And right behind it I have examples, so that would also be conservation of momentum, pool billiards, car crashes, in general all kinds of collisions. Then energy can be defined as a capacity for doing work and so on, and that of course is the conservation of energy. And then again I have examples. This one doesn't have to be collisions, but I have like an automobile here example, I have a residential example, so that goes with the conservation of energy as well. And the third one, we haven't come across it yet. That'll be in the chapter on rotation. So the angular momentum of an isolated system remains constant, both magnitude and direction, and so on. And again, I have an example here that also checks the conservation of angular momentum. So for example, ice skaters, the merry-go-round, gyroscopes, helicopters, anything that rotates, rotating machine parts, they take on the conservation of angular momentum. Okay, these are from the worked out problems in physics. So you can just go in there respectively. If you just look at these here, it says force F equals -67. Well, it's probably going to be newtons. There it is. Another force, -19,000 newtons. The impulse, and unfortunately I have to pause. I'm going to get a call here. Okay, I'm back after this phone call. I hope this works out for me. I'm not so well versed in using Collaborate. Okay, so anyway, so here, for example, is impulse. Impulse is force times time, so that'd be newtons times second. However, and when you look here, you actually cannot find that newtons times second. However, the impulse is also the change in momentum, and if you take newtons times second apart, you will come up with kilograms meters per second, which is momentum, and there it is. That's why it takes on that unit. Velocity, of course, is, well, either kilometers per hour or meters per second. If you look at this problem here in the WOPIT, you will find out in this case it's actually kilometers per hour. Of course, I strongly encourage you to look at the worked out problems in physics and actually do them. This one here is just testing that, yeah, you looked at it, and this is basically a giveaway. The way I word it here, you just look at it and fill it in. But again, I hope that you're gonna look at those problems thoroughly and figure them out. Okay, so let's see, this one is in the extra book on elevators. You would need to read through that chapter to figure out which ones apply. I didn't look at it personally here, so I'm just putting in, it's probably something with apparent weight, pulleys, acceleration, that makes sense. Probably force is going to be in there. I'm assuming lift and weight. There's probably an electric motor. I'm just guessing that's what's going to be in the in that chapter when you read it. But you would, of course, have to read it yourself. All right. Let's see, and a few more of those. Here's the mechanical universe. Just like I say here, don't watch these videos over and over again just to get all of these quotes in the correct order. I will notice that if somebody has watched them and they might have just screwed up a couple of them backwards, I will give them full points. But if somebody just randomly puts in an order here, I also notice that too. And then I say, well, you didn't watch these here. I want people to watch these because they have good physics content in them. I do give a couple of them away. So the first quote is, energy is always conserved. And there it is. And the classical mechanics is the sixth quote. And there it is. And if you want me to, I can give a couple of others away. So the vital question is, energy is always conserved, and so on. That's the second quote. I'm going to pause here because I have to cough. Okay, I didn't pause, I just turned the mic off. And the seventh quote here, if I'm not mistaken, is going to be Newton's third law. Gets into the action and so on. But you still would have to watch these. And the last one is, well, in the previous question you were, I think it's an extra credit one. The previous question you were asked, during which decade the mechanical universe was filmed, you probably answered 1980s. And here on what criteria? Well, look at the eyeglasses of the students. Look at the demeanor and looks of people shown in the video segments. Look at the hairdos and clothes. The physics experiments, actually, I could still have them today. For the physics that we're teaching in an introductory physics class are actually almost timeless. They go back a long time, and the equipment might look a little bit different, but overall the physics experiments themselves are timeless. Okay, and that was my recording on the Unit 3 homework for energy and momentum.